Good afternoon, everyone. I'm Shangru from Tsinghua University. I'm honored to be here to present our paper, Demystifying the Security Implication of IoT Device Rental Service. The sharing economy is a growing trend in cities with various IoT devices rental service emerging in our daily life. By integrating IoT controller into useful tools like e-scooters, chargers, and washing machines, these devices can be rented to users without the need for staff. The rise of IoT technology has popularized IoT device rental service, enabling devices to function and be placed without reliance on Wi-Fi or wired connections. Unlike Wi-Fi connected smart home devices, rentable IoT devices can directly connect to their backend servers via cellular networks, allowing them to receive network control command from these servers. This capability enables widespread rentable IoT devices deployment domains without traditional network constraints. Users can rent these devices via their mobile applications. Taking the popular shared bicycle service as an example, users can locate bicycle on the companion application's map and initiate the rental process by scanning the bicycle QR codes. The application resolves the QR code's contents and sends requests to the server to remotely activate the selected device. However, we found that the weak device identifier used by the QR code could become an attack vector. As illustrated in this figure, if the application APIs lack proper authorization mechanism, attackers can exploit horizontal privilege escalation vulnerabilities to remotely manipulate other devices. Unfortunately, some devices adopt short IDs, enabling attackers to easily enumerate them. Consequently, attackers can leverage these vulnerable APIs to manipulate any victim devices by guessing its ID. This attack vector can also extend to vulnerable device server APIs, further increasing the security risk of IoT devices rental service. We conduct a systematic study on the security of real-world rentable IoT devices, covering 17 physical devices and 92 mobile applications. Our goal is to track if the devices are vulnerable to large-scale remote attacks. In this work, we study how adversary can remotely abuse these devices on a large scale. We consider both rentable IoT devices and their companion smartphone application as potential attack targets, focusing on remote exploits that do not require physical access to victim devices. We don't consider attacking local cellular networks or local devices, as such attacks would only impact a limited number of devices, fail to expand the adversary range. Instead, attackers exploit the communication between the device and servers or between applications and servers to maximize the potential impact on device and users. Our only assumption is that the attackers can analyze both IoT devices and applications. To analyze these devices, we first reverse engineer their binary protocol and APIs. We then perform black box API testing to identify access control vulnerability in the device-to-server and application-to-server communications. Finally, we verify this vulnerability can lead to large-scale exploitations through ID enumeration attack. Now we present our first phase of analysis, which aim to uncover vulnerable APIs in the rentable IoT products. To uncover vulnerabilities in rentable IoT devices, we follow a three-step process. First, we extract firmware by partially booting core chips of the IoT devices and capture the cellular network traffic through enabling debug logs by AT commands. Next, we reverse the protocol by analyzing the captured traffic and encryption key extracted from the firmware for encryption messages. Finally, we developed phantom clients that replicated original devices and used the same protocol and credential to reconnect it to the servers to perform black box API testing. Note that this approach is accessible to attackers who can illegally obtain rentable IoT devices for analysis. Our analysis revealed that these devices share common vulnerabilities. Most devices lack hardware protection, making it easy for attackers to analyze their firmware and the network traffic. In addition, a significant number of devices have a common authentication key hard-coded in their firmware, which is a critical security risk. Attackers can use phantom clients to impersonate as real devices and connect to the server if they know the device ID and the encryption keys. First, they can prove the device state by manipulating the health reports sent to the server, making functional devices appear faulty and triggering unnecessary maintenance tracks that can disrupt the rental service. Second, for some devices, reconnecting with the phantom clients can force the original device offline, leading to the denial of service attacks. In addition, attackers can exploit this to stop billing while the actual device remaining unlocked, allowing them to use some device for free. To identify API-related vulnerability in companion application, we proposed a same automated approach to perform black box testing. First, we prepare accounts and log into the applications, manually trigger the core logic by scanning QR codes and select the appropriate UIs to rent and return a physical rentable devices. Meanwhile, all requests are captured by the burp suite proxies. These requests then automatically mutated and replayed in burp suites, which can further expose vulnerable APIs that do not properly track permissions. We discovered 34 vulnerabilities across 23 IoT applications, which can be categorized in two types. For device-related vulnerability, we identify 4 WeChat applications that can manipulate payment parameters to change the amount, change the transaction amount, and 9 applications that can be exploited for remote device control by horizontal privilege escalations. In terms of user-related vulnerabilities, we discovered 9 vulnerable IoT applications that can leak users' highly sensitive data, such as real name and phone number. In addition, 6 applications contain horizontal privilege escalation vulnerability, allowing attackers to hijack user accounts and to rent devices. Now we introduce our second phase of analysis to verify if the previous mentioned single device vulnerability can lead to large-scale exploitation across multiple devices. Rentable IoT products use 3 types of ID. The first type is user ID, which indicates different users, and the third type is device serial number embedded in QR code used by the server to distinguish different devices. The final type is device ID, stored in the firmware and used by the server to authenticate the devices. If there are any access control vulnerabilities, attackers can exploit this ID to manipulate unauthorized resource, leading to large-scale exploitation of device and users. Short ID lead to several large-scale exploitation for rentable IoT products. The reasons are threefold. First, many IoT vendors use the same setting and common keys to their own devices, which can be stolen from the public device. Second, insecure direct object reference vulnerability are very common and difficult for IoT vendors to eliminate. Finally, IoT rental services have too many devices and users for a single product. If they use short device IDs, attacker can easily enumerate these IDs, finding victim device or user IDs and launch large-scale attack by compromising these devices' authentication. We identify multiple real-world products vulnerable to ID enumeration attack that can lead to large-scale exploitation. By enumerating the device ID, attackers can abuse certain physical devices on a large scale, resulting in consequences such as a large-scale device DOS attack and unauthorized usage, including leading EV chargers. By enumerating user IDs, attackers can steal users' data or hijack user account to abuse the device on a large scale in 8 applications. By enumerating device serial numbers in QR codes, attackers can exploit existing horizontal privilege escalation vulnerabilities to manipulate the device at scale in 12 applications. In summary, we successfully uncovered over 50 vulnerabilities in 33 products. We notified the vendors and they confirmed our findings. Most of the vulnerabilities have been fixed, but there still remain some in the old products. To prevent large-scale exploitation due to ID enumeration, we propose a decoy ID-based solution. The basic idea is to insert decoy ID among real IDs. If a client consistently triggers decoy IDs that are high frequency, it strongly indicates that adversaries are attempting to enumerate IDs. We talk to device vendors to understand why they use the short IDs in their product. They use the short serial number in QR code for easy manual trade when the scanning is not possible. They also use common keys across devices to simplify manufacturing, avoiding the need to pair each device's ID with a unique key on their servers. However, this practice allows attackers to guess IDs, increasing the risk of ID enumeration attack. In this paper, we reveal serial numbers in multiple real-world devices that enable large-scale DOS attack and device misuse. We also work closely with vendors to mitigate this vulnerability and propose a decoy ID-based defense solution to counter the threat posed by ID enumeration attacks. Thank you for listening. Any questions?